This is problem 8 in chapter 10, and before you watch the rest of this video, you should review conceptual example 2. And the big thing that you need to get out of that is that if you cut a spring in half, you'll get half the displacement. And I'll review the idea up here. I write F equals Kx. You'll get half the displacement, which means if the same force is applied, you'll have double the value for K. So that's the result coming out of example problem 2 that I'm going to use to help solve this problem. So I've already set up the picture here a little bit, and we've got our spring. This is our 100 coil spring with our K1 and our displacement 1, which was given as 0.16 meters. And now we have two 50 coil springs, so each one of these is 50 coils, and I'll have a K2 here. And the relationship from that conceptual example is that K2 will equal 2K1. So there's one relationship I have between these two cases. Other things I'll do here is I'm going to do some summation of forces. And because I have two cases, I'm going to set this up as a ratio. You could certainly use substitution, but it just lends itself to that because a lot of things hopefully are going to cancel. And since I'm given x1 and asked for in the problem, how much does each spring stretch in the new case, when we replace this 100 coil spring with the cut it in half, the 250 coil springs, I'm going to do a ratio of x1 to x2. So that's what I'm going to be thinking about when I do this problem here. So I'm going to try to answer that question. If I can get a number here for this ratio, since I know x1, I'll be able to easily solve for x2. So I need equations with x in it. I'm not thinking energy because I've just got something hanging from a spring, so I'm going to think forces. And since these aren't going anywhere, I can sum forces and have them equal to 0. So let's go ahead and do a general result of that, and I'll show my work here. So summation of forces in the y direction for both of these will equal 0. Let's do two free body diagrams. We'll come back to that in a second. Let me get my free body diagrams on here. So for my case 1, I'll have force up, force of weight down, and there's only one spring attached here, so I'll just say spring force S. We'll do that. And then for this other case, I have 2 points of contact, or 2 supporting springs. This works the same way for strings, by the way. So I'll have force of spring, we'll call it 1, plus force of spring 2 up, and then the weight going down. So what's happening here, on my picture, I'll draw another little picture here. I have 2 up arrows that are the same size. I'm just going to represent them like that. But there's 2 up arrows and 1 down arrow, because both of these are helping to support the weight. If they were vertical, it wouldn't work that way. But since they're spaced out, they can each support some of the weight. And on top of that, they're also stiffer springs. So I'm going to expect a very different displacement when I get to the answer. I'm expecting something significantly smaller than 0.16 when I figure out this x2. Okay, so let's go ahead and now sum our forces in the y direction on both of these, and they are add up to 0. I'm just going to do this down here. I'll rewrite this ratio later. So I'll have force of spring 1, which will be K1 x1 equals, and the mass stays the same, so I'll just use m to represent that. The mass stays the same despite my horrible picture here. That's the same object. So K1 x1 equals mg. So there's my case 1 equation. And then here, same idea, except I have 2 of these. So I'm going to do 2, and then K2 x2 equals mg. You could also have done K2 x2 plus K2 x2, same difference. It'll end up being 2 of them. So 2K2 x2 equals mg. So there's those 2 up arrows compared to the 1 down arrow. And it's just a summation of forces in the y direction. That's where this is coming from. The force of the spring equals the weight. The force of the 2 springs added together equals the weight going down. Now I'm going to solve those for x. So x1 equals mg over k1. x2 will equal mg over 2k2. And remember, even though these are the same materials, they have different spring constants. The spring has effectively changed. Same materials, just different length. You get a stiffer spring. And that was why we had this. We'll use that in a minute. I'm going to start substituting in, so let me set my ratio up here, and we're almost done. Set my ratio up here and plug in. We've got an mg over k1 over mg over 2k2. The m's will, as we would expect, cancel. The g's will cancel. Rewrite this. I'm going to bring this up top. So 2k2 over k1. Yep, that's right. And now, since the K1, K2 didn't cancel, if I was stuck at this point, I'd have to go back, review conceptual example 2, and figure out the relationship between the spring constants. But we've already done that. It's right there. So now I'll go ahead and substitute in. So for K2, I'll put in a 2K1. So there's my substitution for K2. It's 2K1 over K1. K1s will cancel, and I get 4. So it's going to change by a factor of 4. So x1 over x2 equals 4. This is the idea. We have our value of x1 back given in the problem was 0.160 meters over x2 equals 4. So cross multiply. So we're going to end up having 4x2 equals that, or x2 equals 0.160 meters divided by 4. We're going to get 0.04 meters. Let's double check. Problem 8. 0.04 meters. Yep, that's correct. So it went that down by a factor of 4. We divided what we originally had by 4. And again, it's not just cut in half because of the 2 supporting things, because not only do we have 2 springs supporting it now, but both of them have double the K. So that's why this went down by so much. If you need help understanding this relationship, come in. I have a few other things I can tell you about that. And then after that, it just becomes a ratio with some summation of forces. And this, which we did a little bit with strings, but hasn't popped up too often, that whole, if they're both supporting, you get 2 forces there. That's it.